Welcome everyone to our first video on Introduction to Differential Equations. So we're going to start off in chapter 1, which talks about first order ODEs. You might say, Jason, you have not even told us what an ODE means yet, and have patience. We'll get there very soon. Because it gets even worse, right? Our first section is going to be how do we model with ODEs. And again, we'll get there soon. We're going to start actually very zoomed in, and we'll zoom out shortly. We'll talk about the basics of modeling. When I say I want to make a math model, what am I talking about? And eventually we'll start talking about differential equations. So we have this real life situation. We want to model it with math, and being able to use derivatives makes that way easier. So I'm going to start by writing something down. So let's say we're interested in the growth of a population. Sorry, we're interested in population growth, and specifically I tell you that the growth of the population is going to be proportional to the population itself. This is your first differential equation in this class. Now, it doesn't look like a differential equation. It looks like a pretty simple sentence. The growth of the population is proportional to the population. But if we really break this down, like go back to algebra and break this down into individual pieces, what is the growth of a population? Well, that's the rate of change of that population. What's a rate of change? A rate of change is a derivative. So you might say the growth of the population is the derivative of the population with respect to time. And then again, go back to algebra. What does is mean? Is means equal. And then again, think back to, I don't know what class you learned about this, but proportionality. If something is proportional, that means there's some constant times the value itself. And finally, what is the population? The population is P. So we started off with a fairly straightforward sentence. The growth of the population is proportional to the population itself. And we just translated that into math. That's a differential equation. And specifically, what it is it's a ordinary differential equation. Now, what do I mean when I say ordinary? Well, you may or may not have dealt with partial derivatives, but we are not going to deal with partial derivatives here. These are regular derivatives. These are not partial derivatives, okay? So we're not going to deal with partial derivatives. We're not really going to deal with multiple independent variables in this class. The study of partial differential equations is much more complicated. And really the short answer is that for most partial differential equations, we can't even solve them by hand anyway. In fact, for many ordinary differential equations, we can't solve them by hand. There is no analytic solution to many of these. And we'll actually see one today. So there will be computers, there will be other analysis, and there will be graphical stuff. It should be fun. But yeah, here's a differential equation. Now, I'm never going to write differential equation. It's too many letters. A lot of times I'll write ODE, as you can already see. Okay, so ODE, ordinary differential equation, no partial derivatives. All right. And yeah, so here we have one. And this is actually a differential equation that you've probably seen before in some area of your life. Maybe you've only seen the solution to this differential equation. But let's add some information here. Let's say that this constant of proportionality, let's require this to be positive. If it's 0, this is silly. There's no growth. And if it's negative, then we don't have growth. We have decay, which is fine, but not what we want to talk about here. And let's give it an initial condition. Let's say that the population at time 0 is just some parameter called P0. So we have some starting population. I don't know what that starting population is. We'll call it P0. Then all of this information together is called an initial value problem. Okay? And again, enjoy seeing it right now because will forever abbreviate it after this. as IVP, an initial value problem. Why is it an initial value problem? Because it's a differential equation with an initial value. Okay, so it's a problem that has an initial value. It's an initial value problem. Another thing that you'll see a lot that we won't talk about, at least at the start, is boundary value problems. Okay, we are given information at the two sides of something. Usually those are more spatial. Most of the differential equations that we talk about in this class has time as the independent variable, right? Remember, again, some of your things, right? The input of a function is what's known as the independent variable. The output of a function is known as the dependent variable. And then when you have things like k's and such, right, these are what's known as parameters. They're not variables. We don't know what k is, but it's not changing. It's just something. We'll come up with it later. Okay, or maybe we haven't found it yet, but it's a parameter. Okay, so again, lots of vocab in these first couple videos. Going to try to keep things pretty straightforward. One other thing that I wanted to talk about, we're almost already done this first video, is that this is what's known as a first order ODE. Okay, why is it a first order ODE? It's a first order ODE specifically because it only has first derivatives. Okay? It doesn't have second derivatives. What do you think we would call a differential equation with a second derivative? Probably a second order differential equation. Unless there was also a third derivative, in which case we'd call it a third order differential equation, right? You get the idea. So the order has to do with how many derivatives have been applied. And of course, this differential equation could be written in other notation. This is what's known as Leibniz notation, dp dt, dy dx, right? All of that stuff, that's Leibniz notation. We could also see this, and I know this is getting crowded, but I'm almost done writing, so we'll fit it all on this page. We could also write this differential equation differently. We could write it as p prime equals kp. Right? That's using that Newton's notation. We could also include the independent variable. Sometimes we don't, a lot of times we don't. We could also write p prime of t is k times p of t, right? Using that function notation. Something that you may not have seen before, although you may have seen it in physics, is p dot equals k times p. Now, a lot of times this dot, right, this is a derivative. And specifically, it's used when the independent variable is time. Okay, so this is very commonly used. Math people don't tend to use it quite so much as physics people, in my experience, but seeing a dot directly on top is very common to denote that your variable is time. Here, it's not completely obvious whether your independent variable is time or space. Those are very common independent variables. Time, location, height, width, whatever. But here, this really does say, okay, we're talking about a function that's changing over time. My independent variable is time. So these are the basics of modeling. This is what a differential equation looks like. Again, you have seen the solution to this differential equation already. And in a section or two, we're going to solve differential equations like this by hand. It's quite simple. You'll be pretty happy as long as you remember your Calc 2. There's going to be a ton of Calc 1 and Calc 2 in this class, so make sure you're reviewing, make sure you're refreshing. It's okay to forget, but that means you're going to have to refresh, okay? So we'll have some extra assignments that you can do to review some integrals and review some derivatives. Please do those optional assignments. Yeah, I'm really excited to talk about differential equations. We got some really cool stuff in store for you. In the next video, we're going to talk about what does a solution look like? And it's exciting because, again, you've seen it before. All right, good luck. Bye-bye.